Hello students, I am Snehal Mule. Welcome back. This is our 8th virtual e-learning session on wave optics. Before we start today's session, let's have a quick recap of previous session. We discussed conditions for obtaining a well-defined and a steady interference pattern, methods for obtaining coherent sources, Lloyd's mirror and Fresnel biprism, and optical path. In this session, we will cover diffraction of light, types of diffraction, Fresnel diffraction, Fraunhofer diffraction, experimental setup for Fraunhofer diffraction, and Fraunhofer diffraction at a single slit. Let's discuss diffraction of light. We know that shadows are formed when path of light is blocked by an opaque obstacle. In certain experiment, light is seen to bend around edges of obstacles in its path and enter into regions where shadows are expected on the basis of geometrical optics. We know that sound waves travel around obstacles, as we can hear someone talking in another room even though there is obstacle, say wall, in between. The so-called bending of light around objects is called diffraction. Let us define diffraction. The bending of light near the edge of an obstacle or slit and spreading into the region of geometrical shadow is called diffraction of light. The bending of light penetrates into the geometrical shadow of the obstacle. The light thus deviates from its linear path. Diffraction is noticeable only when the size of the obstacle or slit is of the order of wavelength of light. As the wavelengths of sound waves are larger, diffraction of sound is easier to observe. Consider the examples of diffraction of light. The luminous border surrounding the boundary of mountain just before the sunrise or sunset is due to the diffraction of light. At noon, circular patches of sunlight are seen on the ground when observed from underneath trees. Types of diffraction of light: Fresnel diffraction, Fraunhofer diffraction. Diffraction can be classified into two types: Fraunhofer diffraction, Fresnel diffraction. Fraunhofer diffraction: if the distances between the primary source of light, the obstacle or slit causing diffraction, and the screen are very large, then the diffraction is called as Fraunhofer diffraction. Here, the incident wavefront is a plane wavefront. A lens is required to observe the diffraction pattern on the screen. Fresnel diffraction. In Fresnel diffraction, the source or the screen or both are at a finite distance from the aperture or obstacle causing diffraction. In this, the distances are much smaller. Here, the incident wavefront is either cylindrical or spherical depending on the source. A lens is not required to observe the diffraction pattern on the screen. Let us consider experimental setup for Fraunhofer diffraction. See the figure. A monochromatic source of light, S, is at the focus of the converging lens. The emerging beam will consist of parallel rays resulting in a plane wavefront. These are incident on diffracting element such as slit, circular aperture, etc. If it is a circular aperture, S is a point source and the lenses are biconvex. If it is a linear element like slit, the source is linear and the lenses are cylindrical, so that the focused image is linear. emerging beam is incident on another converging lens that focuses the beam on the screen. Let us discuss Fraunhofer diffraction at a single slit. See the figure. The cross section of a plane wavefront YY dash as shown in earlier figure is incident on a single slit of width AB. The center of the slit is at point O. The slit can be imagined to be divided into number of extremely thin slits or slit elements. The moment the plane wavefront reaches the slit, according to Huygens principle, each slit element becomes the source of secondary wavelets responsible for diffraction spreading in all directions. A lens kept next to the slit converges the emergent beams on the screen kept at the focus. Let D be the distance between the slit and the screen. D is practically the focal length f of the lens. The width A of the slit is of the order of 10 raised to minus 4 to 10 raised to minus 3 meter, and the distance D is of the order of 10 meter. That is, D is greater than A. Let O be the center of the slit AB. There are two sets of parallel rays originating at the slit elements. The central and symmetric beam focuses at the central point P0. Rays parallel to the axis from all points from A to B are focused at the central point P0. All these rays must be having equal optical path. Hence, the path difference between them is 0. They arrive at P0 with the same phase and produce constructive interference at P0. The intensity of light is maximum at the point P0. It is called as central or principal maxima of the diffraction pattern. So in case of point P, at an angular position theta, the optical paths of the rays from A to C till point P are equal because AC is normal to AM. From these points onwards, there is no path difference. So, the rays between AB and AC are responsible for net path difference at P. Look at the figure. The path difference between extreme rays is BC equal to A sin theta. From the figure, BC is equal to A sin theta. Let this be equal to lambda. So, A sin theta is equal to lambda. Let K be the midpoint of AC. OK is equal to half BC is equal to lambda by 2. Hence, the path difference between AP and OP is lambda by 2. So these two rays produce destructive interference at P. In this way, all points between AO and OB will produce destructive interference at P. Point P is the first minimum. This can be applicable for points on the screen having path difference 2 lambda, 3 lambda, so on. Between the extreme rays reaching them, these points will be dark and hence will be positions of dark fringes. Same logic is applicable for points on the other side of P0. At the location of nth minima, the path difference between the extreme rays is a sin theta is equal to plus minus n lambda. At the location of nth maxima, the path difference between the extreme rays is a sin theta is equal to plus minus bracket n plus half bracket close lambda. As discussed earlier, D is greater than A. Hence, theta is very small. Thus, if it is expressed in radian, we can write sin theta is approximately equal to tan theta is approximately equal to theta is equal to y upon d, where y is the distance of the point P on the screen from the central bright point. Let y and d and y and b be the distance of nth dark point and nth bright point from the central bright point. Thus, at the nth dark point on either side of the central bright point, theta and d is equal to y and d upon d is equal to n lambda upon a. From equation 3, theta is equal to y upon d. From equation 1, theta is equal to n lambda upon a. So, substituting these values, we get theta and d is equal to y and d upon d is equal to n lambda upon a. Rearranging this equation, we get y and d is equal to n lambda d upon a is equal to n w. At the nth bright point on either side of the central bright point, theta nb is equal to y nb upon d is equal to bracket n plus half bracket close lambda upon a. From equation 3, theta is equal to y upon d. From equation 2, theta is equal to bracket n plus half bracket close lambda upon a. So rearranging this, we get y n b is equal to bracket n plus half bracket close lambda d upon a is equal to bracket n plus half bracket close w, where w is equal to lambda d upon a. It is the distance between consecutive bright fringes or dark fringes except the central bright fringe. W is called as fringe width. Width of the central bright fringe. The central bright fringe is spread between the first dark fringes on either side. The width of the central bright fringe is the distance between the centers of first dark fringe on either side. Width of the central bright fringe WC is equal to 2y1d is equal to 2w is equal to 2 lambda d upon a. Okay, now it's time that we test our understanding of what we have covered in this session and apply that to the next set of questions. So we have very easy questions at our hand. It is a MCQ. The fringes produced in the diffraction pattern are of dash. You are given 4 options. Select the correct one. The fringes produced in the diffraction pattern are of unequal width with varying intensity. The next one, to observe the diffraction, the size of the obstacle should be dash. Again you are given 4 options. Select the correct one. To observe the diffraction, the size of the obstacle should be of the same order as that of the wavelength. Until next time, happy learning.